In this example, we're told we have a drag force acting on the drag force acting on an immersed object in a flowing fluid is given by the formula right here. This is the drag force. That's a drag coefficient. Then we have 1/2 rho v squared. That 1/2 rho v squared, this bit that I'm highlighting here, that's called a dynamic pressure. That's a term you'll hear in fluid mechanics. Rho is the density of the surrounding fluid, in this case air for this example. V is the velocity of the object relative to the fluid. And A is what's called the frontal projected area of the object in this particular case. It would be the area you would see if you looked from the front, and it's the cross-sectional area you would see. So in this example, we're talking about a bicyclist, so the area here would be the area you would see looking from this direction, kind of the frontal projected area of that bicyclist. And so what we want to know here is how much power must the bicyclist exert to overcome the air drag? And the person's biking at 20 miles per hour into still air. We're told what the drag coefficient is for the bicyclist. This would be found through some experimentation done elsewhere. And we're also told the frontal projected area is 3.9 square feet. You could perhaps find that by taking a photograph of the person from the front and then just looking at the area that the person makes in that photograph. So let's find out the power then to do that. So first of all, to find the power, power is going to be a force multiplied by a velocity. So this would be the drag force, which I'll call D, times the velocity of the bicyclist, V. Okay, so that's how we're going to find the power. In the drag force, we'll just use our formula given right up here. It's just the drag coefficient times 1/2 rho V squared times the area. It's multiplied by V. Now it's just a matter of plugging in all the different values that we have. So we're told the drag coefficient is 0.88. The density of air, we're assuming the person's biking through air, that we would have to look up. So you can look up the density of air at what we call standard temperature and pressure. That's just sort of sea level conditions. So you can look that up. And in imperial units or English units, it comes out to be the following. 0.0765 pounds mass per cubic foot. Again, this comes from what's called the standard temperature and pressure conditions, so STP conditions or sea level conditions. And we just looked that up online. It comes from experimental measurements of what the air density is and what the pressure is and what the temperature is just at sea level conditions. And the units for density in the English system would be pounds mass, so that's a mass, divided by cubic foot, a volume. The velocity, we're told, is 20 miles per hour. Let's convert that over to feet per second, since we're going to be multiplying here with, here it's dividing by cubic feet. And so let's do that conversion. So what is that? 1 mile is 5,280 feet per mile. And then 1 hour is 3,600 seconds. So we can do that conversion, and that should come out to be 29.3 feet per second. And then lastly, the area, we're told the projected area is 3.9 square feet. That's given in the problem statement right here. So we can plug all those numbers back in, and you'll get the following, that the power is 103 pounds force times feet per second. By the way, one unit conversion I made in here is that 1 pound force is equal to 32.2 pounds mass feet per second squared. Again, dealing with these imperial or English units can be a pain sometimes. This is a useful unit conversion to remember because whenever you're converting between mass, which is pounds mass, and a force, pounds force, you can just remember that, and that'll make it a little easier for you. So this is our power. That's kind of an unusual set of units, pounds force feet per second. It's perfectly fine as is, but typically in the imperial system for power we use horsepower. So in terms of horsepower, this is 0.186 horsepower. And for that unit conversion, 1 horsepower is 550 pounds force feet per second. That's probably one you would not memorize. Memorizing this is a good idea. This one you probably you wouldn't memorize, but you can always look it up online. Google is your friend when it comes to unit conversions, and I encourage you to do either this kind of unit conversion approach. This is pretty helpful, or you can use Google to do the unit conversions for you. Okay, I think that covers everything in this example, so we'll end there.